Hello everybody, happy Tuesday. So this is a video that's going to go over the climate review. You don't have to watch the whole thing. Feel free to skip around to the parts you have questions about. And I'm basically going to go through, write the answers down, and I'll post the key. So if you're not sure where the key came from, feel free to watch this video and get any of your questions answered. So this is going all the way back to learning about the atmosphere. 3 reasons the atmosphere is so important. First, it gives us air to breathe. It helps to keep us warm, and we know that because of the greenhouse effect. And we also know that the atmosphere protects us from the sun, from sun's harmful rays. This is mostly happening in the ozone layer, which we didn't get into a lot, but just know that our atmosphere is able to block out a lot of those really high radiation energy waves that come off of the sun. The Earth holds on to the atmosphere through gravity. Large gravity equals large atmosphere. All right, page 2. I'm just going to go ahead and label this. So this big chunk here would be nitrogen. This one is, and we know that's 78%. This is oxygen, 21%. 1% is argon. And then not included in here are the trace gases, which is less than 1%. So then N2, nitrogen has the highest concentration. The smallest concentration would be the trace gases, including the greenhouse gases. And the greenhouse gases fall in the trace gases. So those gases that are keeping our planet warm and keeping our planet too warm are actually in this tiny little fraction of a piece of our atmosphere. And then the last question on this page is to label where high and low pressure would be. So low pressure would be here where it's rising up, because remember that air pressure is the weight of air on your head. So this would be the low air pressure because it's not really pushing on your head, whereas here it's falling, it's kind of crashing down on you. So these two places would be high air pressure. And if we wanted to relate that to the planet, this is where the deserts would be. And this is where the rainforest would be. And if we want to go even further, this would be the Tropic of Cancer if this was north. And if this was south, this would be the Tropic of Capricorn. And this would be the equator. And we know that air is rising here because it's warm, it's less dense, and falling here because it's relatively cooler. So air always wants to be in equilibrium. That should be. This means that if there's a high pressure area and a low pressure area, they will try to equal out. Which way does the air move? It's always going to move from high to low. Think of a waterfall. Think of air being like a liquid, and it's going to flow from the high locations down towards the low locations. And when that air is moving from high to low, so there's the answer right there. When it's moving along the ground, what do we call that? It's my least favorite type of weather. That is wind. So a lot of times you'll have a low, it rises, gets pushed over to the side, falls at a high pressure area, and then it's going to flow from the high to the low in both directions, and this is what we call wind. So when you feel wind, it's just air pressure that's moving, or air that's moving to a different pressure area. Okay, most of the world's rainforests occur along the equator. Why? Because air is rising and less dense, because the sun hits here most directly. So it's really warm. Lots of stuff is rising. And as it rises, it brings up water vapor with it. And as that water vapor gets higher into the sky, it gets much colder. Like if you were to hike a mountain, it gets much colder up there. Brings up water vapor that condenses to forms clouds. And then it rains a lot. So if you want to go on a, summery, sunny vacation, you don't really want to go to the equator. Because it's probably not going to be very sunny. It's going to actually be pretty rainy and cloudy. Where do most of the world's deserts occur? It's about 30 degrees north and south. Those are called the Tropic of Cancer in the north and the Tropic of Capricorn in the south. You don't really need to know those, but if you're wondering what to call them. Why? This is where the air is falling. It's a high pressure. Oh, I should add that here, less dense. But this is low pressure. And there's not any water in it because it all got rained out over here. All the water was rained out over equator. So all that air that's moving is actually relatively dry. And then it falls and it's dry air. So that's where you get a desert. High pressure means sunny, clear day. Low pressure means rainy, stormy. You could have a snowstorm. Anything with precipitation. It's going to be a low pressure, cloudy. And last week, it was sunny and clear skies. It was 80 degrees. That was high pressure. That was sitting over us. So high pressure can be on different scales. You could have it globally, which makes rainforests and deserts. But you can also have it regionally, which makes the weather. All right, so now I'm looking at some graphs. And the first thing that I want to do when I look at graphs is always just to look at the information and just kind of get a general sense of what's going on here. So I've got one Z here and I've got a Y here. So which city is more likely to be located near a large body of water, Y or Z? It's going to be Y. And then use the word specific heat of water to describe why city Y is warmer in the winter but cooler in the summer. Why does living near a body of water make any difference? So I'm going to say water has a very high specific heat. This means it takes a lot of energy to heat up and cool down. This means that in the summer, it will be a cooler city because the water is taking a long time to heat. But in fall/winter, it takes a long time to cool down. And helps keep the city warmer. Something like that. So it's because it's near this body of water, it can't get that cold in the winter. Like the water is keeping it much warmer. But then in the summer, it's much colder. And you can see its peak temperature is actually over here. It's not in July like City Z is. It's actually in August. And that's because it takes so long for that water to heat up that it's not going to be in July. It's going to be in August because that water kind of has, actually, it might even be September looking at this. Because there's kind of like a lag time with that water heating up. All right, difference between weather and climate is essentially time. Weather is day to day, month to month, or year to year. But climate has to be 30-year average. Oops, sorry. All right. And then are the following phrases talking about weather or climate? The first one is weather. T-H-E. Wow. Weather. Climate. This would be weather, probably. This is weather. Climate. Climate. All right, so what four things determine the climate of an area? Latitude or distance from equator. We know that the Bahamas are going to be warmer than the North Pole, excuse me. Elevation. Elevation. We know the top of a mountain is very different from closer to sea level. And then the two that we focused on the most were proximity to water, which we just talked about with the graphs that were kind of like this. Oops, I should probably have that go up a little bit. Wow, that's going to look not that great. And also the, what do I want to call it? Global winds and pressure zones. So that would be like the Hadley cells. Yes, there are natural climate zones. Even without humans, there would still be different climates on Earth. How do scientists know that the climate has changed in the past before humans? Ice core data, which trap air from the past. How are humans changing the climate? Adding greenhouse gases. By burning fossil fuels. Which leads us to fossil fuels. How are fossil fuels made? So before the dinosaurs, dinos, trees and swamp plants were doing photosynthesis. And they were storing carbon inside their bodies, or inside their plant. These plants then fell into the swamp. And over time, they were buried. and buried and basically compressed into oil and coal. And then we extract this and use for products. We are disrupting the carbon system because we're basically taking carbon that's been in timeout for millions of years. It hasn't really been a part of the carbon cycle. It hasn't really been part of the system. It's kind of been tucked away, and we are adding it into our atmosphere. Okay, draw a picture of the carbon cycle. Include at least an animal, a plant, and a human. So there's CO2 in the air. The plant is going to suck in the carbon dioxide when it goes through photosynthesis. Maybe there's an apple, and there's carbon in the apple. And then maybe, there's my apple again. This is a great drawing. Now you get to see my animal. It's my animal. Yeah. And it's going to eat that apple. So now the carbon has moved from the air. The carbon is then going into the trees through photosynthesis, goes into the apple. The apple goes into this animal, which I don't know what it is. Now the carbon is inside this animal, and then if a human comes along and eats the animal, I guess the air should go this way. Now the carbon is inside the human. And then the human is going to breathe out and release that carbon dioxide back into the air. So this is a super simplified version of the carbon cycle. And I'm sorry that my drawing isn't gorgeous. Up to snuff. Okay, what are some common things you use that are made out of oils? Makeup, pens, stretchy clothes, all plastic. And that's all plastic, including water bottles, mechanical pencils. I don't know. I don't know. I'm just looking around the room. Phones, watches, etc., etc., etc. So most things that we use in our everyday lives are made out of oil. Of course, there's gas and things like this. All right, last page. So why are greenhouse gases important for our planet? They keep the planet warm, about 60 degrees warmer than it should be. Planet? Yeah, warm. So that means that we would not have very many warm days without greenhouse gases. Even like a day like as I'm writing this today, it's 80 degrees, which if there were no greenhouse gases, it would actually be 20 degrees outside. So that would be kind of sad. We would never get to wear bathing suits and shorts and tank tops. Draw a picture that shows how greenhouse gases are able to warm up the planet. So coming in, we have sunlight in the visible part of the spectrum. And we have our ground. And then heading out, we have earth light, which is also infrared, which is also heat. So it's coming in as one form, heats up the planet, and then we have to give that heat back. Otherwise, our planet would get too hot. But if it did this, and it did it perfectly, then we wouldn't have any heat left. At nighttime, it would get extremely cold. So luckily, we have carbon dioxides, water vapors, methanes, and when this heat actually hits the greenhouse gases, it warms them up and it re-radiates back to Earth and keeps us warm. Some of it does escape into space, and that's good because we don't want to trap all of the heat. But when it does hit one of those greenhouse gases, which are the special gases, like it doesn't happen with every gas, it will warm it up and then re-radiate it back towards our planet. And that's why on like a really humid day, it feels so hot, especially at night, is because that water that's in the air is basically trapping all these escape routes and re-radiating the heat back to you. So it's usually going to be warmer at night in a humid place than it is in a very dry place like a desert, because it doesn't have all that water vapor to shoot and re-radiate back to you. So if we keep adding more carbon to the atmosphere and burning fossil fuels, what will happen to global temperatures because of the greenhouse effect? Temperatures will rise just by the nature of the greenhouse effect. Basically, it's going to start closing gaps for heat to escape and trap more heat in, causing temperatures to rise. Okay, describe the difference between a positive and negative feedback loop. A positive feedback loop adds to the initial disturbance. And a negative feedback negates the disturbance. And the negative feedback is going to move toward homeostasis. Like we want to be equal, we want to be level, move toward homeostasis, we want to be stable. Whereas the positive feedback is moving away from homeostasis. It's snowballing out of control, away from homeostasis. Snowball effect. And this one is kind of like cancel out effect. An example of a positive feedback loop could be something like temps rise, sea ice melts, lower albedo, oceans warm, sea ice melts, lower albedo, oceans warm, sea ice melts, etc., etc., on and on and on. If you have any questions, I'm going to be upside down.